Pluto is a remote and baffling, more unobtrusive planet that was once a piece of our sun-energized framework's planetary assembly. However, later astonishing declarations by noticeable astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a surprising revelation. They proposed that this cool world is on a potential impact course with Neptune. Yet how is it that this could end up actually working? Furthermore, what may be the repercussions of such a giant event? Are we seeing a fascinating, enormous eccentricity, or is there another thing to this approaching, boundless battle? Join us as we examine the potential consequences of a Pluto-Neptune influence. Pluto, a past planet that was renamed as a dwarf planet, partly due to its shocking orbit, remains a subject of interest and examination in the astronomical community. According to recent figures by leading researchers, Pluto's orbit is hazardously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a potential, risky crash between these two planets that could pose a serious threat to Earth. How is such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our nearby planetary system. It requires an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't, no doubt, completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its especially curved shape, wandering incredibly far from the nearly round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, still up in the air at 17 degrees to the ecliptic plane. How Pluto follows is substantially more inclined compared to other planets. This inclination and elongated nature add layers of complexity to its orbital plan. One of the most interesting parts of Pluto's orbit is its convergence point with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we could expect from their positions in the planetary system. This prompts the regular question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational impacts of other planets. The assessment of Pluto's orbit began not long after its discovery. Initially, astronomers tried to understand its strange path, as compared to planets whose orbits lie fairly close to the ecliptic plane. Pluto's orbit stood apart with its steep inclination and elongated shape. The mystery deepened with the confirmation that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these intricacies is evidence of the complex design of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this problem shows how the orbits of Neptune and the Sun's gravity all connect in a complicated way. The terms libration and resonance, along with the Kozai oscillation, are essential for this riddle. As shown by astrophysicists, what keeps all planets in their orbits is libration. In the particular setting of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is key in preventing their orbits from colliding. Resonance, on the other hand, refers to the periodic movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or some other giant planet, it's arranged entirely above their orbital plane, offering an additional layer of protection from possible impacts. Another critical element of this equation is the Kozai oscillation, named after three researchers, von Zeipel, Kappas, and Lev, who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the Kozai oscillation helps us understand why its orbit around the Sun is so unusual. Despite its seemingly erratic path, Pluto's orbit remains stable for seemingly billions of years. This implies that Pluto's journey around the Sun has a certain order to it, even if it appears eccentric at first. Predicting cosmic events, especially when they involve violent orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainties. While numerical simulations provide a powerful means of understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor mistake or deviation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the tumultuous nature of celestial orbits, like Pluto's, reminds us of the constantly evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto serves as a reminder that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have significant consequences for the stability and behavior of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite these unpredictable forces trying to prevent such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in promoting cosmology, offers an intriguing perspective on the mysteries of our nearby planetary system, especially the dazzling case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's interest in the uncharted realms of space. Tyson's stance on Pluto's renaming is grounded in the ever-evolving knowledge of our solar system. He sees the renaming not as a downgrade, but rather as a significant adjustment in alignment with our developing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He sees the complexities of orbits like Pluto's as an indication of how much there is still to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planetary system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another respected physicist and futurist, offers a different yet complementary viewpoint on the mysteries of space, focusing on the often chaotic forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with visionary concepts, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit underline the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the connections between celestial bodies as an important area of study, not only for academic interest but also for practical implications. The potential collision between Pluto and Neptune, for example, is not just a theoretical situation, but a reflection of the dynamic and often turbulent nature of space. Kaku's futurist viewpoint urges us to consider the broader ramifications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. Kaku suggests that the more we understand the forces at play, the better equipped we will be to navigate and possibly mitigate the impacts of major events. Both Tyson and Kaku's perspectives combine on the idea that space is an area of limitless discovery, and that our current understanding, while significant, is still limited. Their emphasis on the need for ongoing investigation and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now, but also speculating on how they might change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for effective scientific inquiry, cutting-edge technology, and a willingness to adjust our understanding as new data emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a rallying cry for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a broad scientific consensus that for years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational forces acting on them. Therefore, a direct collision between Pluto and Neptune is extremely unlikely. However, The complexities and potential disturbances in orbital elements still mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While the possibility of a Pluto-Neptune impact is largely hypothetical and considered unlikely with current understanding, it highlights the importance of continuous study and observation in space science. Advances in technology, including more advanced telescopes and computational models, will help astronomers refine their simulations and predictions, ensuring that we remain ahead of the dynamic and ever-changing nature of our nearby planetary system. Tyson's perspective on Pluto's renaming, along with Kaku's emphasis on the unpredictable nature of celestial mechanics, both underscore the need for ongoing investigation and a flexible understanding of our universe. The potential impact scenario, while highlighting the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast but still unclear spaces in our understanding of space. Through continued research and observation, we strive to unravel these mysteries, ensuring that our knowledge stays in tune with the ever-developing universe. Pluto continues to captivate scientists and space enthusiasts alike with its distant, mysterious nature. While its status as a dwarf planet has long been debated, its orbit and unique qualities continue to engage researchers. Recent developments have once again positioned Pluto in the spotlight, with the possibility of a gravitational interaction between Pluto and Neptune becoming the focal point of attention in the space community, with Tyson and Kaku bringing this topic to the forefront. The conversation surrounding a potential Pluto-Neptune impact is sure to spark further interest and research. The investigation into these cryptic celestial bodies holds the promise of uncovering new insights into the mechanics of our solar system as we peer further into space. The dynamic and unpredictable nature of our celestial neighborhood only emphasizes the need for vigilance and ongoing investigation. While the potential interaction between Pluto and Neptune remains a subject of scientific interest, it is crucial to consider the broader context of space exploration and the methodologies used to study celestial bodies like Pluto. The discovery of potential risks, such as a possible Pluto-Neptune collision, serves as a stark reminder of the vast complexity and unpredictability inherent in the universe. It highlights the intricate mechanics at play within our local planetary system, where even the most seemingly stable orbits may harbor hidden uncertainties. This thought draws attention to the sophisticated tools and techniques used by astronomers and physicists to understand the movement of celestial bodies. One important tool used in such studies is numerical simulations, which allow researchers to predict and model the behavior of planets and dwarf planets over extended periods by inputting known parameters such as mass, speed, and distance of celestial objects. These simulations can project potential future movements and assess the stability of orbits like Pluto's. Such models often rely on powerful computers and advanced algorithms to handle the massive data and complex calculations required. This method is especially valuable when studying objects with unusual orbits, like Pluto, whose path around the Sun is so distinct from the other planets in the solar system. Moreover, the role of gravitational interactions between celestial bodies cannot be overstated. As mentioned, Pluto's orbit crosses Neptune's, and the gravitational pull between these two bodies could theoretically lead to unpredictable results over very long time scales. However, due to the resonance between Pluto and Neptune, their orbits remain locked in a stable relationship. This gravitational resonance ensures that even when Pluto comes close to Neptune's orbit, they never collide. The physics behind this resonance is fascinating, as it shows how the subtle forces of gravity can synchronize the movements of two distant bodies, preventing catastrophic events like a collision. At the same time, there are still many questions about how other factors in the solar system may influence Pluto's orbit. For example, the presence of other planets, such as Jupiter, Saturn, and Uranus, could potentially disturb the delicate balance that keeps Pluto and Neptune in their stable orbits. These giant planets exert their own gravitational forces, which could cause small shifts in Pluto's trajectory. While these movements are typically minor, over millions or billions of years, they could accumulate and result in more significant changes. This is why astronomers continue to monitor Pluto's orbit closely, searching for signs of any deviations that might indicate a future disruption. Beyond gravitational forces, the influence of the Sun itself also plays a critical role in shaping the orbits of objects in the outer solar system. The Sun's gravity governs the motion of all objects in the solar system, including planets and dwarf planets like Pluto. However, because Pluto is located so far from the Sun's gravitational pull on Pluto is much weaker than on the inner planets, which means Pluto's orbit is more susceptible to external influences. For instance, the Sun's varying energy output over time, such as during solar cycles, could affect the behavior of objects in the Kuiper belt, where Pluto resides. These subtle changes could impact the long-term stability of Pluto's orbit. Another important consideration in the study of Pluto is its environment. The dwarf planet resides in the Kuiper belt, a region of space that is populated with countless small icy bodies and dwarf planets. The Kuiper belt is a relatively neglected frontier, and many of the objects in this region remain poorly understood. As astronomers continue to gather more data from space missions like NASA's New Horizons, which conducted a flyby of Pluto in 2015, we are beginning to gain insights into this distant realm. New Horizons provided remarkable close-up images of Pluto and its moons, revealing a complex world of icy mountains, vast plains, and strange atmospheric features. This data has opened the door to new questions about the formation and evolution of the outer solar system and how objects like Pluto interact with their surroundings. As scientists continue to refine their understanding of Pluto and its relationship with Neptune, one must also acknowledge the broader implications for space exploration and the potential for future discoveries. The study of distant objects like Pluto helps us gain a better understanding of the history of the solar system as well as the forces that shape planetary bodies. Moreover, these discoveries contribute to our ability to predict the future movements of celestial bodies, which could have practical applications for space missions and the future of human space exploration. With ongoing advances in technology, our ability to monitor and study the outer reaches of the solar system is expanding, opening new frontiers for exploration. In conclusion, while the possibility of a Pluto-Neptune collision is highly unlikely, the fact that such a scenario has captured the imagination of scientists and the public alike demonstrates the continuing allure of the mysteries of space. The complexity of Pluto's orbit, the forces that shape it, and the ways in which it interacts with other objects in the solar system all serve to remind us of the vastness and unpredictability of the universe. As we continue to observe and study these celestial bodies, our understanding of the solar system will deepen, revealing new insights and raising new questions. The case of Pluto and Neptune is just one of many examples of the wonders of space that continue to captivate us, urging us to keep pushing the boundaries of our knowledge and explore the unknown. The ongoing study of Pluto and its orbit will likely remain a key area of research in planetary science, as scientists strive to unravel the mysteries of this distant dwarf planet and its interactions with the rest of the solar system. While the prospect of a catastrophic impact with Neptune remains highly improbable, the potential for further discoveries and insights into the dynamics of the solar system makes the study of Pluto and its place in our cosmic neighborhood all the more fascinating.